So let's start. Okay, so let's continue with what we were doing. The last time we kind of just did a problem, which was very elementary. But nonetheless, it's useful. It's going to be very useful. But yeah, let's see what we are going to do today. Okay. So till now, what we have been looking at is we have been looking at functions. Okay, so obviously the title is complex differentiation. Okay, so far we have been looking at functions from C to C, or sometimes we just look at functions which are from some regions in C to C. Okay, open regions, we will define them again and more rigorously if needed, but for the time being, just C to C or some regions. Many naturally occurring functions are of this nature. We saw that this can also be seen in as a function from R2 to R2. And this perspective can be useful. Okay. R2 to R2. So to begin with, there is really no difference. Okay. There is really no difference a priori between functions from C to C and functions from R2 to R2. Okay. So I should say formally, there is no difference. Okay. So then why is it that we are studying complex analysis? Why is it that we are looking at functions from C to C? If they're just functions from R2 to R2, then why do we need C to C especially? If any function from C to C can be looked at like this, right? You can just take the real part and take the imaginary part, and you can write it like this. Then why is it that why do we consider, and then why this? Anyone has thought about it? It's a very vague question anyway, but still. Yeah. No, yeah, I square is equal to -1. That's right. But my point is that as a function, right? As a function, you can just view it like this. Right? Then why do we say functions from C to C? Why do we need to do that? Okay. So, well, that can be said. I think that can be answered in several ways. I think what you have said is that I square equal to -1 is kind of like it's kind of like this, right? If we view, so the real thing is that the complex numbers have multiplication, right? Complex numbers have multiplication. So if you look at two functions f and g, which are functions from C to C, right? Then you can multiply them. You can multiply them, you can do more operations, and so on. Okay. But more than that, the real reason would be, in my opinion, is that, see, if you view a function, if you can view a function from R2 to R2 as a natural function from C to C, okay, meaning that if you can view a function like this, which is like this from R2 to R2, but if you are able to view it as the input coming from a complex number, and that complex number and something happening to that complex number itself as a whole, and the output coming out. Okay, if you can view a function from R2 to R2 in that way, okay, then it's like a special function. Okay, so my point is that functions, okay, functions that can be written, once again, can be written naturally, okay, can be written naturally in terms of the input, okay, being looked at as complex number, being looked at as a complex number, because a complex number unifies the x and the y coordinate in some sense, right? But theoretically, again, formally it does not, right? But it kind of does, right? Because it's just z is being looked at as a complex number. Okay, so these are the things. Okay, we will also see a little later, okay, that there are some natural functions from R2 to R2, okay, meaning that you have the plane and then some sort of a, maybe, you know, some sort of a field acting on the plane. It could be like a magnetic field, some sort of a force that kind of spreads across the plane and kind of morphs the plane to something else. Well, again, a plane, the output is a plane theoretically, but morphs the plane, and that kind of function is naturally a function from C to C. Okay, we will see these things. Okay, and the idea and thing here is that these functions, which can naturally be written as functions of a complex number z without breaking up the real and the imaginary parts, without needing to break up the real and the imaginary parts, are the functions that will usually turn out to be complex differentiable. Okay, those will be the functions that will usually turn out to be complex differentiable. Okay, I will later on try to give a different motivation for how do we arrive at the definition of complex differentiation in a natural way. Sorry, I mean, from a physical perspective. From a symbolic perspective, obviously, just take the definition of differentiability and just replace real by complex. Then you get the definition. So symbolically, obviously, you're guided enough. Okay. In any case, so let's come to this, and then let's come back to what we were looking at and what was our goal. Okay. So here we had a function from C to C, and well, in the short term, the goal is that we want to get a simple criteria, okay, simple criteria for f to be differentiable. At this point, let me just say complex differentiable. Okay, I'm not using the word holomorphic at this point. Okay, just saying complex differentiable. Holomorphic is slightly different, as I mentioned. Yeah, and we already have the criteria, okay, which is a necessary criteria. Okay, a necessary criteria which we have already derived the last time. Again, it turns out to be in terms of u and v, in terms of the real and the imaginary parts, right? It says that you take the real one and you take the derivative with respect to x, or you take the imaginary part and you take the derivative with respect to y. They are equal. Okay, and so this is not the only one. And this is equal to so what was the, so uy and obviously v, yeah, second function with respect to x, yeah, right, negative. Okay, so do we remember this? So a necessary condition means that if f is differentiable, obviously I mean complex differentiable at a point x naught comma y naught, then this should happen at x naught comma y naught, and this should happen at x naught comma y naught. Okay, do we all remember this? Okay, can anybody quickly summarize as to how we arrive at this? Now one can arrive at this in several ways. We have kind of seen slightly two different ways, but can anybody just how, like a quick just a description of Not the details, but how one would, what's the idea behind. Yes, just think about like how would you end up with these equations? Even just computationally, you can run it in your head and think. So the situation is that, look, we are assuming that f is differentiable. Okay. We assume that f is differentiable, complex differentiable, and we arrive at this. How do we? Okay. So there are many ways. There are many ways to get it, but the simplest is to just use the definition, right? Just use the definition. Okay. Let us just do it, because then we will also see more that there are some other kind of other necessary conditions in this. So assume that f is complex differentiable at x0, y0. What does that mean? Let's call this z0. Okay, then we know that this is what we call this limit, which is existing because of our assumption. So we are assuming, see, this is the usual way in which you get sufficient conditions. Eventually, when you say a criteria should be able to, I mean, we are more interested in, if you're, so in general, if you're describing, trying to come up with a criteria for something, okay, usually we are more interested in the criteria being able to say, yes, something is complex differentiable, or yes, this graph is connected, something like that. Okay, so that's what is known as sufficient conditions, right? Obviously, if something is not complex differentiable, then your criteria, your sufficient criteria may not be able to describe it. Okay, so all that is fine, but how does one naturally land upon it? Obviously, if you are given that, okay, this is the sufficient criteria, please prove it, it's fine, you can just go out and try to prove it. Okay, but how do you arrive at it? We are kind of seeing that process also here side by side. Okay, because this just runs parallel in wherever you look. Okay. So usually, see, suppose this is the space, this is the place of objects that you're interested in. Okay, so let's say this is the complex differentiable functions. All the complex functions are here. You have polynomials, you have 1 by z, and you have many other, well, there are actually not many other. They are all quite constrained. They are all analytic in sense, but let's say these are your functions. Okay, when you're describing a necessary condition, then what are you doing? Okay, you are describing some condition, like this condition, right? This is kind of creating a block. This is the space of all functions which satisfy this Cauchy Riemann equations. These are obviously called the Cauchy Riemann equations. Okay. So the way we arrive at sufficient conditions is we start with necessary conditions. Right? Necessary conditions are easy to get. Right? You assume the process works, and then you try to look at the process from different angles, specialize it in different ways, and you get these criteria. Right? This bigger blue one is the CR equation. So it is those functions which satisfy CR equations. Now, obviously, because it's a necessary condition, it will obviously engulf the complex differentiable functions, right? But then what happens is you look at this necessary condition, and then you put other necessary. So usually that's the way, right? You put other necessary conditions. Okay, well, not always. Sometimes you cut it out more than what's needed, but you would usually, I mean, the most desirable thing is to, put other necessary conditions. So you may put other necessary condition, maybe that u is differentiable, v is differentiable, and maybe some other conditions. And if they are nice enough, then soon you will land on exactly this if you take the intersection of those conditions. Right? And if along the way all of those are necessary conditions, then what you're going to get eventually is an equivalent condition. Right? So this is roughly what is what usually we desire, right? But it doesn't usually happen. Okay, it's very hard to usually get a necessary and sufficient condition unless it's a very discrete thing. You know, it's a very sharp thing, sharp edged thing. So you cut it out easily and you get the thing. Right? That usually happens in discrete, but it happens. No, it happens. Okay, but that's the best thing, but that doesn't usually happen, right? And you can also understand, right? I mean, if this is your object of interest, okay, so this is the interest object, and you start with a necessary condition like this. Okay, now if this is a necessary condition which is not sufficient, and if there are counterexamples in all kinds of directions, okay, and if you give another necessary condition which has counterexamples in all kinds of directions, okay, so there are functions which are, so maybe for this there will be functions in which u is not differentiable and v is not differentiable, but then there may be counterexamples. So if there are all kinds of counterexamples, then usually it will be difficult to cut out a sufficient condition, keeping everything necessary along the way. Okay, but if your object of interest is like this, and you start with a necessary condition which is not sufficient, but it is, so this bigger one is a necessary condition. It's a necessary condition, but it is taking care of one aspect of the situation. Okay, and similarly, if you can come up with another necessary condition which takes care of the other aspect of the situation, then you are in a better place to end up cut out a sufficient condition. Okay, so you have to see. So this is how mathematicians, like, they are able to guess, right? I mean, that, oh, this looks like it's going to, looks like just one more necessary condition will be enough for this. And no, we have all kinds of counterexamples. That's why counterexamples are very important. At this stage, it may be difficult for you to internalize this, but you must at least take away this. At least the first thing, the thing is that counterexamples are very important. What kind of counterexamples are you getting? Are you getting counterexamples in all kinds of directions, different kinds of counterexamples, or is it only one kind? Then you know that, okay, the other necessary condition I need is to remove those counterexamples, and then I may end up with a sufficient condition. Okay, but usually this doesn't happen. Usually what happens is we have the object of interest, we take a necessary condition, but then we have other random conditions. Okay, we take other random conditions like this, and we cut out this part, sufficient condition. No, it is sufficient, but maybe it is not strong enough. It will only capture a small. So this condition, these two conditions together will help you to say yes, but they may say no in places where it is complex differentiable. Okay, so it's a say, I mean, this is a too general thing. This because this captures what we do in throughout mathematics. Not much useful things can be said, at least now, but maybe later on in logic, using this along with maybe some topology, you can say many interesting things. But in any case, coming to this, the idea is that you want to start with necessary conditions and you look at what's going on. You have this necessary condition. Now, because you are allowed to tend to zero in all kinds of ways, you obviously tend to zero in the real. So you tend to zero along the real axis and you tend to zero along the imaginary axis. And with both those two things, you equate them and you get this. Okay, so just work it out. That's pretty easy. But let me just do one thing, one side of it, because we will see another necessary. It's not, so it's never a harm to keep adding more and more necessary conditions. Okay, so when you're trying to derive sufficient, from what the diagrams we have seen, right? When you're trying to derive sufficient condition for something, it's no harm if you have a lot of necessary conditions. Okay, finally, you're not going to lose anything. You may have a lot of conditions, all of which may not be useful to test in the end, but at least you will not, I mean, if you keep adding necessary conditions, you will not lose any object of interest because you're always being outside the thing. So that's why it's okay to look at more and more necessary conditions. We're not going to lose much. So in this, if we so yeah, if we take h to be real, we will see some other very obvious condition, but maybe we have not even said about that at all. Okay, take h to be real. So h is real, just real, so it is h comma 0 in that sense. But yeah, if you take h to be real, right, then it means that you are not changing. So now we write it in that language, we have to write it in that language now. It's like, you have this, you're not changing the y naught. Okay, so this is the part coming from f of z naught. This is the part coming from f of z naught plus h. And then, I'm sorry. So then we take the v, and once again, we are only changing this. Comma y. And we are, it is h comma, it's a mod because it's h comma 0. In any case, yeah. So this is what we have, right? Now we, 1 minute. So once again, so if we keep it, no, this is complex differentiation, right? So we just keep it h mod because so see, so this, let's call this I, yeah, this should be the way it was, right? And now this limit exists, right? This limit h goes to 0 exists. So we all know this, right? That if this limit exists, then the real part limit should also exist and the imaginary part limit should also exist, right? So what this implies is that all partial derivatives, meaning that you understand, they take the derivative of u with respect to x or with respect to y, and for v also, okay, all partial derivatives should exist. Okay. And the other thing which you would see if you just keep h arbitrary, okay, if you just keep h arbitrary, and this I think, okay, this is something which I had said at some point in the past, so I thought I didn't say, but we said, is that if you just keep the h arbitrary, don't make it real or complex, or don't make it purely real or purely imaginary, but then just still separate the real and the imaginary parts, you would see that you would get that u and v must be real differentiable. Okay. In fact, we have also proved that it means that u comma v must be differentiable as a function from R2, as a function from R2 to R2. Okay. So all those things are necessary conditions. Okay. All those things are surely necessary conditions. Okay. Now let us just collect them and then see if they are sufficient. Okay. So remember, we have put other conditions. Okay. If we do not put them, then it will not work, and it will not be sufficient. So let me remove this thing and put. So surely only the Cauchy Riemann equations are certainly don't seem to be enough, right? Only the Cauchy Riemann equations don't seem to be enough, and they are not enough. Okay, with some other mild conditions they will become enough, but okay, only these two equations are not enough. Okay, plus, okay, plus f is real differentiable. Let me just put this. Okay. So if you have all these three conditions, I mean, just at the point, so we're not asking for anything more. We're just asking at the point x naught comma y naught, it must be the case. Okay. So we have just added more necessary conditions for safetyness. Okay. In fact, only this is not enough. We will see counterexamples, but maybe we'll see that because I want to really do the proof today, because otherwise we'll have to push it to the next step, which is not good. Okay. So only these two conditions are not enough. We need to put this other obvious necessary condition. This is again this obvious necessary condition. Okay. Now, before we go into proving that this is sufficient, okay, we will not actually approach it like that. But my point is that before we go there, let us just try to understand what this means. Okay. If f is a function, let's just take function from R2 to R. Okay. Let us clearly try to just define, because we'll need this just in the proof. If you have a function u from R2 to R, okay? So this is just a surface and such, right? It's just like a polynomial in two variables and so on. So no need to draw the graph. This is what it is, okay? When I say that u is differentiable at x naught comma y naught, can anybody just, if I know that formally we know the definition, but just to review it, and also we'll see it in a different way, which is the way we'll use it in the proof. So can we just quickly define what this means? U to be differentiable at x naught comma y naught at a point x naught comma y naught. Yeah, we must know the definition. So just the partial derivatives existing is not enough. Okay, just the partial derivatives existing, like the partial derivative of u with respect to x and the partial derivative of u with respect to y. Okay, just those two things existing will not be enough. Okay, so we'll look at the definition of this. So it's very straightforward. Okay, and I have described that in several ways, and we have also arrived at the condition in a natural way and so on. But let us just define it. The definition is this. We would demand that the limit of h going to 0, in this case, h is, as it's there in the notation, it's just a pair of numbers. It's just a point in R2. Okay, it's limit. What we are saying is that you take this thing, take this difference, okay, and then there should exist, okay, there exists a comma b, okay, such that there should be an a comma b, should be a comma b, such that the dot product, maybe say 2, the modulus of this, okay, divided by the modulus of h1 comma h2, the modulus of h, same thing. Maybe since we are throughout writing that, you can just write h1 comma h2. Okay, that this should go to 0. This limit is 0. There should be some a comma b such that this limit is 0. Obviously, the a comma b is unique and so on. Those are actually the partial derivatives. Okay, but this is the definition. Okay, this is the definition. But this definition is not very, it's a very formal definition, but we want to just tweak this a little bit, okay, so that we can write it in a more approximation based way, which is a good way to see, see the derivatives. Okay. So how can we say this in a different way? We say, okay, what this means is that this is the limit being 0 just means that this is a function. Okay, I'm just using a notation which is there in the books. So the book I'm following up is Cauchy, taking the main content from there and trying to say based on that. Obviously, this just means that there is this function. This is a function, okay, such that this goes to 0. Okay, and we can say more. That is. No, so we don't need to put the mod, right? We don't need to put the mod on the numerator, at least put it in the denominator. Can just say this. Okay. The size a function of h and so on, and this happens such that, so you know that, so here limit of psi h goes to 0 is 0. Okay, and this is what it is. Now, why is this more natural? Because this says that okay, the nearby points around x naught comma y naught can be approximated by the point x naught comma y naught and a linear function. and a very simple function, which is just multiplication by scalar h, and the rest is just very, very small. So a function is real differentiable if and only if you can write it like this. Okay, so function is real differentiable if and only if you can write it like this. We can further simplify this. We don't need to write the language of vectors. We can just say AH1 plus BH2. That's it, right? So this is what we are going to start with. We are assuming that f is real differentiable, which means that u and v are real differentiable. Okay, so let us see. So let's start with this equation. Okay, this equation just is saying that u is real differentiable. Okay. So this is u is. This way to write the fact that something is differentiable is very useful, proving chain rule and many other things. Okay, it really captures the essence of derivative, that is linear approximation. So now what's the plan from here? What we'll do is we have all these necessary conditions, right? These conditions in here, this, and this. We will just try to integrate those conditions. We'll just, meaning that we'll just try to combine those conditions and see what we can say about f from these conditions. Okay, that's the goal. Okay, we'll combine these conditions and see what we can say. Okay. So these are the conditions that we have. So now what we want to do is we just look at it like this. Combine the conditions to say something about, say about f. Just think of it like this. Okay, and it's very, we'll see how we can combine, because we want to say something about f. Okay, so first of all, this is the thing, this is what we start with, right? We can further improve, we can further say a more specific thing. As we had said, we can replace the a and the b. So the a is just the partial derivative with respect to u x, right? That is what this is. And the b is the partial, maybe I should also be more precise here for now and say that this is at, so first obviously there was the derivative is taken, then this times h1, okay, plus this times h2. 1 minute. It's about u, right? So y, again at x naught comma y naught, h2. Okay, so we're just trying to combine it and see what we can say about f. Simple. And here we have this approximation. This is the error. And this is h. Just setting single mod, you can understand. Okay, so this is obviously the first equation. What is our next equation? Obviously about v. V is also differentiable, so we take it. Okay, so that has become, we said the same thing about it. Second, so just write the same thing. See, so the way we are doing this is just natural. It just makes it look natural. Okay, this is just combining it, writing the definitions, obvious necessary conditions. So I'm just writing it. And then there's another, okay, there's another function. Obviously, we must remember that psi1 and psi2 go to 0 as h goes to 0. So are there any questions so far? No? Okay. So now the combining part. What is the thing? How should we combine these two equations to get F, just to get F in the picture? Yeah. Just ask yourself, how am I going to combine F? How am I going to combine these two equations to get F in the picture? Let's just write it here. F of u comma iv is u of, sorry, f of x comma iz s comma iy is equal to u of, just writing s comma y, I of s comma y. It's the same thing, but yeah, let's write it like this. Doesn't matter. So how should we get f? No, it's very straightforward, right? We just need to get the I in the picture. Just multiply this by I. There's just no other way. This is no other way to do. This is just the only thing to do, right? Multiply this by I. Like obviously, right? There's nothing else to do. And then obviously add them. Then we add these two, right? Just add them. When you add the equations, yeah, obviously we add the left hand side, and what we get f of z naught plus h, right? We get f of z naught plus h. Yeah, so we are using h to denote this general thing, h1 comma h2, right? That's what we get. And what do we get here? We get f of z naught. What do we do now with the other things is important. Yeah. Let's see what we can think about that. So a priori, I just write this. I'll just not write the x1 comma y naught, it's just the same throughout. If you just add them, so we just get this. But then what more do we need to put? So we are moving towards f becoming complex differentiable. Right? We are moving towards that. Yes, please, any suggestions? So remember, we have this, but let's also try to picture the final result. Okay, let's try to picture what it would be like to achieve, right? So if you just picture the final thing, then what is it in this way along these lines? How would it look like? Because maybe you're still thinking about derivatives as the usual definition, right? But if we also, just like I explained this more linear way to write what real differentiation means, whether in multivariable or single variable. We can also do the same thing here, and we have also seen this earlier to explain, this angle preserving nature of such functions. So it's very simple. We're saying that we want a number. It's just a number, right? You want a number so that this is obviously complex multiplication or just h, but yeah, you see this is what we want. This is what we want, right? And you can see there is a, obviously, sorry, this is not. And we also want some function here, small function. I'm just writing a psi here, not psi1 or psi2, it's just a psi. So because something different maybe, yeah. We want this again, obviously, times so should I put h or mod h or 1 minute? It does, does it matter? 1 second. I think I'm making some mistake. Not mistake, but should I put a, yes, so I can take a mod here. Yeah, and that's how I will get, because I already have the mod, I can't get. You see, this is what we want finally. This is the thing. So how do we get this? We have a part of it. Remember, these are our assumptions. These green things are our assumptions, right? These are also our assumptions along with the differentiation which we have used. So far, we have only used that. So we should also see what all we use exactly. Okay, so that's not immediately needed, but we have only used the fact that u and v are real differentiable at x naught comma y naught, not nothing about in a neighborhood and so on, just at x naught comma y naught, which is the same as saying that u comma v as a function from R2 to R2 is real differentiable at x naught comma y naught. We have used that so far, but we also have these all important conditions. How do we put them? How do we use them in our situation? Okay, we had further seen, right, that if this is the complex, if this is the complex derivative, then it will also be equal to, so what will this complex number be, right? Yes, simply that. That's what you have to do, right? Just substitute them in the equation. Yes, because this is what it will be. This is what that complex number is going to be, right? Because you can just take the derivative. No, so this is not what it will be. It will be taking derivative with respect to x of the entire function. So okay, it's not hard to get. So what it will be. Yes, but yeah, simply speaking, we don't need to write all that to start. We just substitute. Simple as that. So we substitute with the plan that obviously maybe, but how do we, what should we have in mind while substituting? So this del u del x and del v del y. So let me just try, let's try to, so since I've written this, it doesn't matter, but yeah, we can try to remove del u del y, right? So I'll remove del u del y by minus del v del x. So let's just do it in the next line. And no, hold on. One second, just 1 second. Making mistakes, right? This is del v del x. Sorry. Yeah. Okay. Yeah. So we wanted to get rid of del u del y and del v del y, right? So yeah. So we'll replace the del v del y. Again, it won't matter. You will get the same thing in the end, but yeah. Del u del x h1, and again I want to remove this, so I will write minus wait, sorry, I'm making mistakes after mistakes. So we'll just keep this. I think we don't need to touch that even, because this is what it is. I need to change this. So yeah, del u del y is minus del v del x plus I, and this will just become del u del x. Yes. I hope, yeah, this is correct now. Okay. And we have obviously, we have made another mistake. We have, no, we have not. We have the I, so that's fine. No, so that's all right. Now we're kind of there. Okay. So I'll just remove this. So remember, we have just, this form of the way to write the derivative like this is very important, because then we can start, dealing with derivatives just the way we deal with numbers, and just the way we deal with usual equations. So we are there now. Or, yeah. This, and so what should we do now? We have, so do we need to do anything? No, right? This is exactly what we need. Yeah. This is exactly, if you just expand this, and this is exactly what that is. So you can just check that. And this is exactly what that is. Okay. So yeah, so that's it. That's, hold on. I mean, so this is H1, and this is this, and this is IH2. So if I put a I, yes, so you can check that. Yeah, this is what it is. All right, and so this is our psi, and this is our H. Okay. So we have done, which implies that F is complex differentiable at, okay. So we have done this rather slowly, but we now understand how it really comes. Okay. And what is exactly needed. So in a lot of places, you will see that they will say, obviously they also prove stronger things, but maybe they don't focus on the small part. It's sometimes assumed that on an open set, means in some region, okay, on an open set or neighborhood, that U and V are continuously differentiable. Okay. So they are differentiable and they are continuous, which implies that they are real differentiable and so on and so on. But, and then they prove this, but we have proved it in the most minimal way. So we will see the other ways in which this can be written, and then we'll also, that will be a chance to look at counterexamples and such. Okay. But we have seen just what's the least sort of required, right? At the point, these are obviously necessary conditions. Okay. This, and this. These are all necessary conditions. We know this, seen that, and then this is also a sufficient. These three together combined is also a sufficient condition. Okay. Yeah. Okay. Right. So that implies F is. So, yeah. So we have finally proved that the Cauchy Riemann equations plus F being real differentiable at x naught comma y naught implies F is at x naught comma y naught. So remember, we have only proved that it is complex differentiable at a point. Okay. Now, complex differentiable at a point is not a very interesting thing, because that does not imply it something called analytic. That doesn't imply that it will be like a polynomial. Okay, only at a point. But only when you assume complex differentiation in a neighborhood, meaning that you assume that a function behaves well in a neighborhood, is when the good things start happening. Okay, so that's that. And there are reasons to expect that. Okay, but for the time being, let us let us just get into the counterexamples and those kind of things. Okay. So 1 minute. Yeah. So let me state this. Okay. U and V, which is usually what is given in the book. So one has to be careful that this is not really necessary. Okay. If you are only wanting it at a point. Okay. U and V need not be, okay, need not. So I want to say that derivatives, it's called continuously differential, but yeah, derivatives of U and V, derivatives of U and V need not be continuous. Okay, so we do not need to assume that the derivatives of U and V are continuous. Okay, now what does it mean? What does the derivative? You see, if you take a point x naught comma y naught, okay, then what is the derivative? What is the derivative of U? I'm not looking at the partial derivatives. Okay, I'm looking at the derivatives. Now we know that the derivative is a pair of numbers. Right? For example, at this x naught comma y naught, we got a number, right? So when you want the derivative of a function from R2 to R, U and V are functions, U and V are functions from R2 to R, right? Then at every point, the derivative itself is a vector, right? So the derivative of U, the derivative of U becomes a function from R2 to R2, right? This need not be continuous. The derivative need not be continuous. Okay. The derivative will exist, obviously, that's needed, obviously, but it did not be continuous. Okay. Yeah, if you're only asking at a point, otherwise it will be, but that's really hard. That's a hard thing to prove. Okay. The next thing is, which is more commonly seen, is that the partial derivatives of U and V with respect to x and y both, yeah, x and y need not be continuous. Okay, so these are some more simpler things to understand, right? This function, this function, this function, and this function, right? These need to exist, obviously. Again, these need to exist, but they need not be continuous. Okay, they need to exist, but they need not be continuous. Okay. Yeah. Okay. But can anybody say that why, if all partial, and this is usually the way in which you will get these things. Okay, if all partial derivatives are continuous, okay, if all the partial derivatives are continuous, and obviously that's always we are assuming, and satisfy the equations, and continuous at x naught comma y naught, obviously at x naught comma y naught, and satisfy the Cauchy Riemann equations, then why does that imply that f is complex differentiable? Yeah, can we quickly prove this? Because this is usually the form or the way in which it will be given to you. So all the partial derivatives exist, not just exist, but they are also continuous. Okay, and they satisfy the Cauchy Riemann equations. Then why is it that is enough? So remember, I'm not assuming here that U and V are differentiable. I'm just assuming that the partial derivatives exist, which means that you approach along x, the derivative exists, you approach along y, the derivative exists, and they're continuous. So please try to prove this. This is in fact a very, it's just coupling This what we have proved with the previous result. Okay, so this is not something profound in the sense that this is just something that you have already proved in the past. So what this means is this basically, if all partial derivatives are continuous, then that actually implies that u and v are differentiable. Please try to prove this. Okay, real differentiable. Okay. So if you have the function u, so let's just look at, yeah. So what I'm saying is that if u is a function from R2 to R, if just look at one at a time, u is a function from R2 to R, this exists and continuous, then that implies that u is differentiable. Okay. Real differentiable, obviously. Okay, try to prove this. You will need so the way we prove it, yeah, just think about it, try to prove it. Okay, I had also proved this in earlier class, much earlier. I think it was in lecture, it was in class 2, I think second class or third class, I think, yeah, something like second or third, whichever is there. But just try it out. Okay, try to prove this. So the partial derivative is being continuous applies. Okay, but only the partial derivatives existing is not enough. Okay, that is what I want to show. Okay. So if, so this one must understand, if these things, if these guys all exist, this, and then with respect to y to x exist, and they satisfy the Cauchy Riemann equations, this is not sufficient. Let's try to get a counter example. Okay, so just those objects in which these things exist and this is satisfied, they are not enough. So what I'm trying to say from here is that only this things existing is not enough. You need something more. Okay, yeah, I should have just written, I don't even need to say this, right? I just want to say that this is not enough. Okay, this will not imply complex differential. Only the partial derivative satisfying the condition is not enough. You need the partial derivatives either to be continuous, or you can even have something weaker, which is the partial, the u and v being differentiable. Yeah. Let's just do this one. Let's think about this. So these things are not addressed in Stein-Cauchy. Okay, because usually they are interested in a differentiation in a neighborhood. Okay, in which all the things turn out to be true. I mean, in the sense that then all the partial derivatives become continuous. They become even differentiable, second differentiable, third differentiable, everything just happens. Okay, so then these points are now more important. And complex differentiation at a point, as I said, it doesn't really capture much physical phenomena, doesn't capture natural things, even that arise in mathematics also usually. But they are very important from the perspective of examples and counterexamples, at least, and maybe other places also. But usually whenever a complex function is differentiable at a point, you will see that it will be differentiable at a neighborhood. Okay, but then that's what makes these questions important from exam and example counterexample perspective. Okay, let's think about this. So I'm saying that this will not imply. So we want a counterexample. We want something which satisfies this, but not complex differential. So let's think. We want to think how you can make this condition true. Yeah, you want to think how you can make this condition true, and think of a just first thing, the easiest way to make this condition true. Just constructing counterexamples, right? So make this true. It's very easy. Just make a function in which all of these are zero. Yeah. Obviously, if it's zero function, it doesn't work because it's also differential. Right? Yeah. But we want, and we also have obviously a point where we can look at, right? So we can make a function for which all these are zero at some point. Okay. So make them zero. That's what we want. Okay. But then we also don't want it to become differentiable. Okay. We don't want it to become differentiable. So what kind of functions can we look at? Means not complex differential. So as we have said, right, those functions in which, those functions in which the real and the imaginary part kind of get separated. Yeah. Those kind of functions will not be complex differentiable. Okay. And what are some natural examples? For example, you can take the function z going to z bar, this function, right? So if you consider this function, I'm just trying to see, okay, this will not work. This will work. No, this will not work because the partial derivatives. Yes, if you take this, you will see why this will not work. So if you, this is a function, right? If you look at this, is not complex differentiable, so it's a good candidate to take. But if you take the derivatives, partial derivatives, if you take this with respect to, if you take, this is the u, this is the v, right? So if you take u with respect to x, the problem is you get 1 and such. Okay, so then maybe the Cauchy Riemann equations are satisfied. Okay, are sorry, not satisfied because they are 1 and then that will be -1. So it will not work, right? It doesn't satisfy the Cauchy Riemann equations. Okay. So that is a problem. Yeah. So we can just check it again. So till this is 1, and this with respect to y is obviously 0. And so v with respect to x is 0, but v with respect to y is -1, right? So we want del u x to be equal to del vy, so that is not happening, right? And we wanted, and so del uy and del vx are matching, but these two are not matching. This and this are not matching. So how could you make it match? So maybe for that, yeah. No, if you do that, then these conditions may not be satisfied. Okay, it might still work. You may be able to come up with it. Okay, you may be able to come up with that. But I'm just taking some natural examples. And but can we just tweak this and make it work? If we make this also, no, but then it will be complex differentiable. If you make it plus, then it will be complex differentiable. Yeah, so this does not work. 1 minute. Yes, so if you take a branch, no, you can take something easier. I think you can take you can just take something like you take the z, so this is u comma v, and you can just take it to the mod and make it differentiable. Yeah, so you can just take something like this distance and such. Okay, so yeah, try to take, so it uses function. This function will not be complex differentiable. Okay, you can check. So what is this? If you want to write it as z, you see, if you write this z, then obviously you understand that this is, z plus z bar by 2 and z minus z bar by 2 and so on. Okay, this kind of function can never be complex differentiable. Okay, there's a z bar here. You can also just put in, just use the definition and check. So use the definition and check that this is not complex differentiable, but nonetheless, all the partial derivatives will be 0 at 0, 0. Okay, you can check that and you can kind of feel that, right? Because at least one of you or we will remain in the numerator, right? So yes, so that should work. So just check that. Okay, something like that should work. I could have also just written that in the way of x plus iy and so on, but yeah. So check that this is not complex differentiable. Okay, not. So I mean anything that has a z bar. Okay, anything that has a z bar, and maybe we could have taken z going to mod z. I'm wondering. Yeah, if we just take this, this is obviously again not complex differentiable. This will work, but please check this. This is like a thing that you should do it. It's not complex differentiable, but it satisfies these things. This, but the only problem with this may be that so at x at 0, 0, when you take the partial derivatives, yeah, one has to check. Okay, what happens to the partial derivatives at 0, 0. But these kind of things you can manage and you can get. Okay. Right. Okay. So that's it for today. Rishabh, did you have any specific branch function in mind that will have partial derivatives to begin with? Yeah. Okay, yeah. Okay, so but that is not specifically okay. Okay. No, this is nice. Yeah. So z bar by z. And why have you taken a z in the denominator here? Okay. So then if we, yeah, so this, yeah, but one has to check if this works. So we can, it should be not difficult to check. Yeah, one has to check it. Okay, so please check. So if you want to check the partial derivatives, usually you have to check it at 0. But will the partial derivatives exist at 0 for this function? Maybe yeah, because you put this. What? It is a? No, but still the partial derivative may not exist, right? It may not. Yeah. So unless you check it. Yeah, so you can just check it. Just check if this works. Okay. Check. Yeah. Partial usually. So what is the intuition behind the partial derivative being 0 is that the function is lying down. Yeah. Right. This will, because this will go to 0 much faster. Yeah, and then there is a, yeah, so because this goes to 0, numerator goes to 0 much faster, the partial derivatives will be 0. Yeah, that already looks correct to me. That's right. Perfect. And also it will not be complex differentiable because of the conjugate. Right. This will work. Yeah, I think, yeah, conceptually this will work. Just check the details. Good. This seems to make sense. Yeah, this will go to 0 much faster. The partial derivatives has to exist. Yeah. Nice. That's conceptually good, well made. Okay then. Thanks. So we will continue. Like we'll do a class, not this Monday, we will have it on Tuesday because Raghav has a problem on Monday. We'll do it on Tuesday and then Wednesday and Friday. Okay. Yeah. Okay then. Thanks. Yes. Yes. We will do it. Yeah. But I just felt that we were a little since we were not even able to do the easier versions. Okay. Yeah. But next class we'll surely do it. Okay. Next class we'll surely do that. Okay. Because it's not very hard, but yeah. And yes. Okay. Thanks. Thank you.